So in the last class, I have given already the theoretical part on the ticket centers, and we already discussed how to design this PN junction using the ticket centers. Means I have given the theoretical demonstration. So all of you are requested to put up your microphone as well as your camera. Okay. See, in the last class, we have taken this is the structure, and we are going to design this structure using the ticket centers, and we have considered these are the dimension. See, briefly, I will again demonstrate the same structure, how to design and how to extract the electrical characteristics of this PN junction from the simulator. First, I will discuss that part. Then I will discuss the MOSFET, how to design the MOSFET. The similar way you can design the MOSFET. As I told, if your software is already open, first I will close it. See, simply what you have to write, first you have to open the software. For this one, you have to write the SWB. That means Central's Workbench. You have to open. Okay. See, after that, this window will open. Means you can see this window will appear on your screen. As you can see, this window is appeared. Is it or not? As you can see, this is your Central's Workbench window. So this all the this is a project. Here you have to create the project. Then here you can view. Then this is the main part. Extension. This is the main part. So this part you can visualize the result as well as you can design the structure also. Okay. So like this, as you can see, this is the under the stem file. All the device structure, all the whatever device I have created previously, that is already there under the stem file. See, it is the location of the file, location of the software, root, desktop, under the is there. That is the location of your file. And if you follow this, if you go through this manual, as you can see, what you have to do, first you have to create the project. First part is what you have to create the project. Then for this, you have to go to the project, then new project. Okay. So this window will appear. As you can see, there is no tool is added in this window. No tools are there in this window. As you have discussed in the last class, we need two tools. One is an SD, another one is a S device. So in this case, what you have to do, as you can see, there is no tool. Then you have to add the tool. First, you have to add the SDE tool. SD tool. In this SD tool, you can design the structure of the PN junction. For this, you have to go to the No tool. Then you can right click there, and as you can see, this is one option is there Add. Then this window will appear Add tool. Then you have to go to the tool. Then as you can see, there are lots of this is for your process. There are process simulation also like this. Other S process, then your SD, then like this your SD device EMW. But here we will use only this. One is SD, another one is S device. SD means this will give the what structure, as we have already discussed in the last class. This will give the structure and the various electrical characteristics you can extract from the S device. Okay, then first we'll design the structure. For this, we add this SDE file. Then select the SD and click on the OK. Okay, this window will appear. Okay, this is the SD. This is already now added to this SW. That means Central's Workbench. This SD is added. So the next part is what? Next part is you have to construct the device. For this, what you have to go? What you have to do? You have to go to the extension on the top of the window toolbar, and you have to click on the Run Central's Structure Editor. As you can see, this is the extension window on the top of your this SWB. You have to click there and you have to click on the Run Central's Structure Editor. Okay, you have to click on the Run Central's Structure Editor. So this blue color window will appear. As we have discussed in the last class also, after this blue color, a graphical user, a GUI window will appear with blue color background will appear. Okay. So now we have to design the Now you have to design the what structure. See, one point is noted here. Always you have to click on the extract coordinates. Okay, see, you can see here it is written something. Here one box symbol is there with red color. The name is your extract coordinate. You have to click on the extract coordinate to draw the diagram. So all of you are requested to put up your microphone as well as camera. So this window will appear. Next is what you can do. Next step is what? As you can see, what you have to do, you have to select the material. By default, silicon will be selected. See, it is already silicon is selected. But if you need some other material like germanium or any other gate material, like for MOSFET, you need the oxide material SiO2 or HFO2. You can use those material also. But for this purpose, we are using only silicon because PN junction we will get by using the silicon material. We have chosen this is a silicon material. Then what you can do? It is next what you have to do. You have to create the structure. Then you have to go to the 2D create tool and select the rectangular region. You have to go to this draw. Then under this draw, 2D create tool and select this rectangular region. You have to select this rectangular region and drag the mouse over this blue color window. You can see this is your vertex. This is the first vertex. This is your second vertex. Okay. As you can see, we have considered the structure is what? The PN junction structure. We have considered your channel length of the PN junction is 300 nanometer and width is your 50 nanometer. As you can see, if we consider this is a one coordinate 0, another coordinate will be what 0.3 and 0.05. See, in the centers, all the dimensions are given in micrometer. 0.3 means what? It is 300 nanometer and 0.05 means what? It is a 50 nanometer. Like this, we'll select, we got this window. Then suppose this is your, I have given this is a first vertex is 0, first vertex is 0. Then the second vertex will be what? As you can see from this diagram also, the second vertex is 0.3 and 0.05. 0.3 and 0.3 and 0.05. 0.3 means 300 nanometer length X and Y is your 0.05. Then click on the OK. This window will miss this region will appear in your blue color window. You can zoom it also. You can see the XY plot also. If you click on the XY, see this is your X, this is your Y, this is your Y. Okay, like this you can zoom it also. Similarly, you can rotate it also. Okay. Okay. See, this is your first you create the rectangular region for your to construct the PN junction. We have considered this is your silicon material we have taken. So next is what? Next, what you have to do up to whatever we told, your y-axis positive in this case in the downward direction in the central ticket. In the last class also we have discussed the same thing. Next, what you have to do, you have to set the contact. See, this is your what? This is your PN junction. That means you need the anode and the cathode. Now, next we have to set the contact. For this, you have to go to the contact and contact set. For this, in this blue color window, you have to go to the contact and you can see first option is a contact set. You have to click over there. This contact set will appear. Okay. Next thing, what you have to do, you have to give the name. You have to give some name like anode or the cathode. You have to give some name like anode and the cathode. Suppose I have given first name as your anode. Okay. Suppose first I have given this is your anode. And this is your what? These are your H color. H color means what? Like this. This is H color means what? Suppose 100 is blue color, then 000 is your green color. Like that, 8 combinations colors are there in case of your central stick. Okay. Like this, there is some your S thickness. You can by default it is given your 4. You can change it also. Like this, there is some face pattern also. As you can see, these are the various pattern of the face. Like this, there are maybe 1, 2, 3, 4, 5, 6, 7, 8 patterns are there. You can select various pattern for various your, like for anode we have select one pattern, like similarly for cathode also you can select one pattern. Okay, like this is a anode. Then what you have to do, you have to set it. You have to set it, automatically it will be added. Okay, automatically it will be added, the anode is added. Similarly, you can add the cathode also. Cathode, suppose I have given this H color is 101, and the pattern also I have changed this pattern. Okay, you have to set it. So after setting it, it is also you have to activate the contact. It is mentioned, click on the anode and click on the activate of this window. That means I have to activate this contact. You select on the anode and activate it. Okay. Similarly, you have to select on the cathode and activate it. Okay. After this, what you have to do? You have already given the anode and the cathode in this PN junction. Then you can close this window. You can close this window. Okay. See, whatever we are doing, all these commands are appearing in this below window. You can see all the commands are appeared in this window. Next is what you have to place the contact. You have to place the contact on this blue color, this GUI window. Then at the top of the window, material list already have selected. And see, from this one, it is mentioned, click on the top and you have to select the edge. You have to select the edge. You can do it like this also. You can select the edge, okay, like this. In the material list, what you have to do, which will select the body. This one you have to select the edge. Okay. Suppose what will happen here, after selecting this edge, you have to click on this left side. Suppose you have to click there, and after clicking there, take your cursor on this and click there, and it will appear as orange color, and click on the right click. Okay. Similarly, see, this is your basically actually what happened here. You give the position of your contact, like anode and the cathode. Sometimes it will show some error because of see, actually what happened. Actually here you can right click and it will show which one we are going to select, like anode and the cathode. Like this here also you can select which one you are going to select, like anode and the cathode. Here it is already select the here it is already select what this is your. This will be your actually cathode. Okay, this will be your cathode. Okay, similarly here you can select this is your anode. Okay, so all these things are appeared here. This is a select, this is a cathode and this is a anode. Next step is what you have to give. You have to define the doping. That means because PN junction means there should be a p-type material. You have to dope. Similarly, you should have to dope the n-type material. So like this, what you can do for this, what are the steps? You have to go to the mesh. Under this, you will get these options, REL oblique EVL window, and you have to select the rectangle. What you have to do, you have to go to the mesh, then this window, and you have to select what? Rectangle. Okay. After selecting the rectangle, what you can do, like the previous case, here also you can drag it. Okay. See, what is your means as we told means your PN junction structure is this one. Up to 0 to 150 nanometer is your p type, and 150 to your 300 nanometer is your n type. Then for this purpose, you go to this. Suppose this is your vertex 0 0. Only you have to know the coordinate system. This is your 0 0. This is a first coordinate is 0, 0. Suppose we are going to define the p-type region. This is 0, 0. N-type region is what 0.15 and 0.05. Okay, last coordinate is what 0.15 and 0.05. Okay, this is your suppose p-type material. Next is what similarly you have to define the n-type region also. Similarly, you have to define the whatever you do for p-type, you have to define for n-type also. Your p-type length is what 150 and width is 50 nanometer. Like n-type also, length is 150 and width is 50 nanometer. Similarly, here also you can define it mesh this then rectangle, and this is what this first coordinate is what in this case this is 0.150 and then what 0.03 0.05. Okay, 0.15 and 0, then another one is what x is what 0.3, then y is your 0.05. See, this is your what? This is your n-type material here considered. Okay. See, next what you have to do? You have to giving the doping concentration. That means you have to dope your p-type material some group 3-type semiconductor, n-type material by group 5 semiconductor. For this purpose, what you can do? You have to like here all the steps are mentioned. You have to go to what? You have to go to the device, then click on the constant profile placement. You have to go to the device, then constant doping placement. This window will appear. Okay. So under this one, see there are two into one is one, another is two. See one is for what? See here you can see one is for your here you can see one is for what? Your p-type and two is for your n-type material. Suppose we are going to first dope by p-type material, then you consider this is your boron. Here lots of means like n-type material concentration also there. Because this is your p-type, we have considered boron as your doping material. And you can consider the doping concentration amount is suppose it is mentioned 1 in 90. Like this here also you can give this is 1 in 90. The amount of doping concentration is 1 in 90. Okay. Then you have to click on the add placement. All the things are mentioned here. Click on the add placement. That means the p-type is doped with boron with concentration of 1 in 90. Similar steps you have to do for your n-type material also. For n-type material, what you can do? Like this, here you can give some name. This is your 2. And for n-type, here you have to select this REF AVL window 2. And suppose this name also you can give 2. And n-type it will be doped by what? Arsenic group 5 semiconductor. And you have to click on the add placement. Okay. Like this, you have to dope both the n-type and the p-type material by corresponding your boron and the arsenic. Next is what? After that, you can close this window. Then this is your p-type and the n-type p-n semiconductor. That means p-n junction diode you got. Next is what? You have to define the mesh. For this mesh, what you have to do? You have to go to the mesh. Then like it is also it is mentioned here, you have to go to the what? You click on the your mesh, then refinement placement, then a window will appear. Under this window, you have to define the mesh size, like it is mentioned. The maximum size is your 0.003, that means 3 nanometer, and minimum size is your 0.001 1 nanometer, and for both x as well as the y. Okay. Similarly, here also you go to the mesh. Then this window will appear. Sorry, mesh. Then mesh. Then refinement placement. This window will appear. Okay. So like this. This is for 1. Like this, you can define the maximum mesh size, suppose 0.003 and 0.001. Sorry, 0.003. This is for x and the y. Similarly, for 0.001 for x and 0.001 for y, minimum meshing size. And you have to click on the create what? Create refinement. Create this refinement. You have to click on this one. See here, one thing what you can see here, it is showing only one window. That means only for either p type or the n type it is showing. But we have to look for both your n type as well as the p type. But there may be some issue, I think. That's why it's not showing. But whatever may be, we can edit in the command also. Okay. Then you can close only in this case. Only we look for the p type. Okay. You can close this window. Next is what? After that, what you can do? Finally, you have to click on the, you have to view the mesh. For this purpose, you have to go to the mesh, then build mesh, and you have to click on the build mesh. Okay. So after build mesh, this is the structure. Only you can see this is the your doping concentration only, and this is like this. This is the doping concentration. Okay, we'll visualize this on later. Okay, this is the structure. That means success. As you can see, on means meshing is successful. That means structure is created successfully in this case. Next, what you have to do? You have to take this code. You have to take this code from this window to this our SD file. Whatever the SD we have added in the Centra's Workbench, in that one you have to take this code from this window. Okay. For this purpose, what you can do? The normal process, you have to select all these commands. For this, you have to click on the Control A and Control C. But no need to close this window, you just minimize this window. Then you open your Centra's Workbench, and here you right click on this SD and click on the edit input and open the command window. See, this window will appear. In that one, you paste this code, whatever you copied from this blue color window. Okay, whatever you code copied from here, you paste it here. See, next is what? Next is what? There is some unnecessary code is there. Okay, you can modify the code. For this purpose, see the symbols like this, ST, getter or hash bracket, you can delete this code. Similarly, body, these things also you can delete. Similarly, there is something under your inverted comma, those things also you can remove from the code. Like this, suppose we have to remove this whatever getter then one thing you can do, you can go to the edit and replace. Edit and the replace, and from this one option is the replace with. You can select the replace with. Suppose replace with getter, then you can replace, you can click on the replace all. Not replace, so find next. It's not working actually. Some option is there. You can replace, that means you can remove whatever unnecessary code is there, you can remove those code. Oh yes, you have to write it here. Okay, find what and click on the replace all. Like this, we don't need this data then also. You can select it, you can write it here and click on the replace all. Like this, we don't require this hash key also. Hash key also. You write it here and click on the replace all. Okay. Okay. So next, what I told, you can see this is also not required. This is required when you going for the 3D device. This body and this inverted comma also not required. And there is some error. Those things also you can delete. Let's see what. Okay. See, like this here also, these things also you can meshing successful. These things also you can delete. This is also not. So what happened? You can visualize the code. Okay. Now you can see the code. So this is your first silicon material that you have considered, 0 to 300 nanometer with 0 to 50 nanometer. Like this you have considered. And this is the anode and the cathode that we have decided the contact. Okay. See, this is the position of your anode and the cathode. See, this is your cathode. Okay. But here the anode position is not mentioned. Is it or not? There is some means while you are doing the coding, that means while you are constructing the structure at that time, there is some mistakes. That's why this, as you can see, previously there is some error. That's why the anode is not created. So what is the location of the anode? As you can see from this, you can write it manually also. As you can, the location of the anode is not, suppose this is 0, and you can consider the middle of this one, suppose 0.025. Okay, like this is your what? You can write simply this is your 0, and you can name this one is your anode. Okay, this is anode, and this is a anode 0.025, and this is a cathode what? 0.3 and sorry 0.15, 0.025. Okay. No, sorry, this will be 0.3. As you can see from this one, your cathode will be what? Axis of 0.3, and if you consider middle of this device, it will be what? Your 0.025. Okay, like this is the anode and the cathode. And as you already discussed that what you have to define the region for your what and P type and the N type. This is for what? As you can see, this is from 0 to 150. That means this is for your P type. But here N type it is not added. You can add it also. Just Control C and Control V, and suppose you can give. Then what will be the structure? It will from your 0.1502 to 0.3 0.05. Then point sorry 0.15 x is what? Sorry 0.150 to 0.3 0.05. Okay, this is your 2. That means this is N type, and this is the your what? As I said, this is what your P type doping concentration, and this is your N type doping concentration. This is 1 for P type and 2 for your N type. Similarly, you have to define the what? You have to define the your meshing also. As you can see, this is the meshing for your 1. Similarly, you have to define the meshing for your 2 also. Okay. Make it Control C. You can define this is your machine for 2. Similarly, you can give this name also 2. Like this is the structure. Then you can close it and you have to save it. Okay. Next, you go to the workbench and you can see the command. So all this command it is saved it here. Okay. Next, what you can do, you have to run this code. Then you have to right click on this one, and there is some option run. You click on the, okay. But we have not saved it. I think. See, before that you have to save the project. First you have to save the project, but I have not saved it. For this one, it is mentioned temp. You have to write suppose under this backslash, and you have to give the suppose the project name I have given PN. Project name I have given PN. Okay. See, now you can see actually while we are constructing this structure, there is some error in the structure. That's what meshing is successful is not showing. So you can see in this structure up to cathode it is showing, but the anode part is not showing. See, it is like this, the step is same only. See, when it is failed, when it is failed, when it is failed, it will appear as your red color. If it is successful, then it will appear is your what? Your yellow color. Like this, see, the code is same only. Whatever the code, it is same only. Like this, the steps you can repeat again. What happened while I am constructing this anode and the cathode, there I do some mistake. The step is same only. Then similarly, I have this code also. You can directly use that code directly. Let's see. So now it's appearance meshing. This is successful. Meshing is successful. Actually, what happened while you are doing the constructing the structure? If there is some, if you are doing some mistake while constructing your position of the contact or any other mistake, then it will appear as this command will not appear meshing successful. If it is successful, then it will appear as in what meshing is successful. Okay. So next is what you can directly close it. Okay, as you can see, this will appear as what your yellow color. That means this is success. Okay, whatever the code is there, it is successful. Next part is what? Next part you have to visualize the result. Okay, so for visualizing the result, you have to add what your edge device symbol. This is for SD. Next, you have to add the edge device symbol. Select the edge device symbol like the previous step only. Here again, now you can close the structure. This structure, you can close it. Okay. See, this is a workbench. Next, you have to add the what edge device. Then for this, you have to go to the add. Then click on the add tools, and here you can see this is your edge device symbol is there. It is written for your device simulation. Click on the okay. This is edge device. So under this edge device, before means writing the or before using the command, first you have to add the material. Suppose you have to go to the what for this purpose you have to right click on this edge device and click on the edit input, and here is option is the include materials. Include materials. As you can see, there are lots of materials are there. But in this case, we have used only silicon as the material. Then from this one, you select the silicon as the material and select this silicon and click on the OK. Okay. See, by default, you can see the silicon material, it will appear as like this. Okay. The silicon parameter file, that means it is added in your structure because you are using only the silicon material in this case. Okay. See, next, you have to next step is what you have to write this command. You have to write this command. Okay, this is your what? This is for a physics section. This is for a physics section. That means what? As I told, physics section means what? We have to define the Fermi type distribution, mobility, recombination generation, etc. Or you can visualize the plot also. Means whatever the current density, SIC combination, then band-to-band generation, various plot or energy band gap. Those things you can visualize. For this purpose, what you can do, you have to click there, then edit input and command. Okay, this window will appear. See, next, what you can do, see, this is the command, whatever the command is there, it is already there in your centralized device what manual. You can go through this command, the various meaning also mentioned in the your that manual. Okay. So we will directly copy this command from here because this is a physics section and you can directly use this command. It is when I have already saved it somewhere. Then I will directly use this one and you can paste it here. As you can see, As you can see, this is what, this is your what, this is your input file. See, the input file means what, that structure that you have created. This is your that structure file pn2. If you open this file, then you can see here name is given pn2. Okay, the name is given pn2. That means this is your structure file, and this is your what, HDevice.par means what, this is your parameter. This is your what, parameter file. That means whatever the parameter, like for silicon, there is some energy band gap, mobility. Those are what, various properties of your silicon material. If you call this parameter file, then it will automatically take the various parameters of the silicon material. And these are the output file. Output file, any name you can give in, but it's better to give the same name to avoid the confusion. If you got some confused, so for that purpose, you can give the same name. And this is the anode and the cathode. In this case, we are varying the cathode voltage from, suppose, 0 to your 1 volt. Sorry, anode voltage from -1 to 1 volt. Okay, from -1 to the 1 volt. Okay, okay. Cathode we kept at 0. And this is your physics section, like Fermi type distributions we have used, and mobility, doping dependence mobility we have used. And this is for your recombination and the generation. And these are the various plot section. You can visualize the plot like the current or various electron density, SRS or band-to-band generation, those things. Okay. And this is your solve part. Okay, up the gate voltage, or sorry, the anode voltage will vary from -1 to 1 volt. And next you save it. It will automatically ask whether you want to save it. You have to close, you have to click on the yes. Okay. Next you run it, right click it here on the device and click on the run. And it will ask whether you want to save it or not. You have to click on the yes. Okay. Okay. So while it is running, it will appear as what, your this, as you can see, running means it will appear as your what, sky color like this. Okay. When it is yellow color means successful. Red color means what? Red color means what? It will appear as failed. See, now it is running. You can see the result also. See what happened if you right click on here. If you right click on here, you can see this is the standard output. That means you are getting the for various anode voltage like 0.46, 0.45, the various current you are getting. It will be show. It will display here. Similarly, if there is some error, you have to click on this standard error option, and you can see whether there is any error or not. You can see the standard, from the standard error, you can see the various error. Okay. So it will take some time to run your program. That means to get the output, it will take some time. So in between it, some questions I think came. Sir, tell how we can add the compound semiconductor which is available in the tool. So the compound semiconductor, as I already have means told, that which is available in the tool. If it is available, you can directly add it. See, if you go to this one question scheme, if you go to this run Centrus editor, you can see from this material section. From this material section, there are lots of compound material also there, like gallium arsenide or you can see like this gallium nitride or your gallium, indium, antimony, then gallium arsenide antimony, like this gallium indium phosphide. Okay, lots of compound semiconductors are there, whatever you want. Okay. Yes, the question is which is not available. Yes, so which is not available. So for that purpose, what you can do, you can use any material. Okay. So what you can do, suppose you can use the any. Suppose you are using this any other material, but you have to replace those material characteristics by what? Suppose you have to use some material that is not available, and but you have to know the characteristics of that material. For that purpose, you can use any other material, and you have to go to the your parameter file, and you have to replace by the various properties. Means suppose you are using the any X material, it has some energy band gap or mobility or all those things. Then you have to go to the parameter file, and that parameter file is available where you have uploaded the software in the under the material section, and you have to open that material, and then you have to write those various characteristics of that particular material that you are going to use. Okay, I think this run is over. This is over. Okay, see this appears yellow color means the run is successful, as you can see. So next, what you can do, you can visualize the result. For this purpose, you have to go to the extension. You have to go to the extension and click on the Run Center as Visual. Run Center as Visual. Then those steps also mentioned it here also. Okay, you have to check only these two files. One is TDR, one is .plt. See, you have to click on the Run Center as Visual. Then this window will appear. See, it is one symbol is there with file. If you open this file, then what will happen? There are mainly, as we said, the output as .pn2. One is a .plt, another one is a .ttr. If you select .plt, then you can see this will appear. And suppose you are doing the anode voltage, and this anode voltage you can plot a x-axis, and the current, the total current, is plot on the y-axis. You can see this is mentioned left y. We are plotting to the left y-axis. Okay. As you can see, this is your current versus voltage plot for your PN junction silicon diode, and you can see up to your 0.7. This is your knee voltage. Then it increases like this. Okay. This is your what? Diode current for your PN junction. You can plot in the log scale also. If you click on this log scale, it will appear as log scale. See, this is the corresponding log scale plot for your PN junction. Okay, and this is the linear scale. Whatever is appeared, this is your linear scale. Similarly, from this one, you can see the here it is on option is the probe. So from this probe, you can extract the various currents. Suppose X means what? In this case, your diode voltage. Suppose it is 0, then if you click on the apply, then you can see the current value at diode voltage 0. Similarly, suppose at 0.2, what is the voltage? What is the current? If you need, then you have to write 0.2 volt here, and you have to click on the apply. You will get the corresponding current. Suppose at 0.7, what is the voltage? What is the current you got? If you click on the 0.7 and if you click on the apply, you will get this is the corresponding current at 0.7. Okay. So like this is your what current diode versus diode voltage versus current characteristics. Next, suppose you can visualize your various electron or the like other plot also. Then for that one, you have to open your TDR file, the .TDR file, or you can visualize the energy cables. And see, if you want to delete this file, that means if you want to remove this file, then you have to click on this one, and you have to click on the Ctrl D from your keyboard. Okay, then that will automatically. See, as you can see here, it is mentioned this is the various parameters like the absolute electric field in this PN junction. Then your band to band generation in this PN junction, like your band gap narrowing. Then other primary electrostatic potential also there. This is the potential variation in the your PN junction. Similarly, this is your, you can see the SRS also there. See, this is the SRS recombination. Okay, this is the plot for your SRS recombination. Suppose similarly, you can visualize what your electrostatic potential also. See, this is your suppose electrostatic potential. But how you can plot the electrostatic potential? Suppose we are going to plot from this throughout the whole PN junction, PN diode. Okay. See, here some option is there, X and the Y, cut X, cut Y. You can select from this cut X and the cut Y. You have to take the cut line. You have to click on this cut line and click on this PN junction. Okay. As you can see, this is the corresponding electrostatic potential that we got from your this around the horizontal axis. Suppose you need the what around the vertical axis, then what you can do? In which cut line you can select? You have to select the X cut line. See, for that purpose, you can remove this cut line also. See, you have to select the X cut line and click on this junction. See, this is the your cut about this means vertical axis or around this junction, around this PN junction. This is the electrostatic your potential. Okay. Suppose you need the what energy band gap, then what you can do? For that purpose, you have to click on this one. You can see there is some option and a plot energy band diagram. Then you can click on this energy band diagram. It will ask for the option. Do you want to continue? You have to click on the OK. You can see this is the corresponding energy band diagram for your PN junction. See here what happened. Here lots of ECP and conduction and the valence band appeared, because in this case what we did, we have taken the two cut line. One is like this, another is like this. That's what multiple time, as you can see, EC1, EC2 or C2 like this it's appeared. Okay. See, next is what these are the various plot. Like this, you can visualize the other plot also. Like this, suppose you want to see the band-to-band generation, then there option is there for your band-to-band generation. You can give it this cut line. Okay, suppose you take the cut line like this. This is your band-to-band generation plot. Okay. See, next is what next how you can extract this data. See, suppose we want to extract the data from the simulator. Suppose you plot the gate voltage, your diode voltage versus diode current. This is the X plot, this is the X axis, and Y axis is your current. Okay. Next, I have to extract this data. For that purpose, you have to select this one. Then you have to go to the data, and here option is the export XY. Export XY, and you have to click this one. Okay. And you have to click on the export, and you can save it somewhere. Suppose I am going to save it on the desktop. Suppose I have given PN ticket. I have given the name as PN ticket. Okay. This is the export of the data. Like this, you can see I have given the name as PN ticket. Yes, this is the file. See, this is your what? This is the corresponding your diode voltage versus diode current plot. As you can see, these are the various values. You can take it in MATLAB or the Origin software to plot the result. Okay. Yes, this is your PN junction current. Okay. So up to this, whatever we discussed, that is your what PN junction. How to see the characteristics and how to extract the data. See. Next I will directly show the, suppose this is on MOSFET. Suppose this is on MOSFET structure, and this is your source length is 100 nanometer, and your channel length also 100 nanometer, drain length also 100 nanometer, with this 100 nanometer, oxide thickness is 40 nanometer. Like this we have considered, and this is silicon, SiO2, and gate material. Okay, gate. This is the, as you know, the MOSFET. This is the suppose body part. And this is the oxide, and this is what? This is your metal. As already discussed in the previous lectures, this is the basic structure of any MOSFET. Okay. Suppose we are going to design this structure. I will directly show the structure. See, here it is already already I did it. Suppose this is the MOSFET folder. If you open the SD file, you can see This is the silicon that you have considered. This is the silicon part that you have considered, and this is your SiO2 part. That means above the silicon, this is the gate oxide material, and this is the gate polysilicon that you have considered. And this is the source, gate, and drain body. This is the source, gate, and drain and body. Okay. See, like your, in this case, we need the contact for what? Source, gate, drain, and body. That means this is a source contact, drain contact, gate contact, and this below this is a body contact. Okay. So next, this is the position of your what? Source, drain, and not position. This is the window, because to define the what? Your doping concentration for your source, drain, body, and the channel. This is for, suppose this is one doping window, like this 4 window are there. Suppose this is what? This is your, I have considered this is what? This is your source, this is body, this is your again drain, and this is your what? Channel. Okay. And these are the various mesh that you have considered. Okay. And this is the your, like this is your the last step that you have found. This is the mesh size that for going to 1, 2, 3, 4. Like for channel, source, drain, and body. Okay. So suppose in this case we are going to run this structure. Then you can see the structure. Like the previous steps, you can run it. So this is the corresponding MOSFET structure that you have considered. This is your total. This is source, drain, and this is channel. This is your body part, and this is your oxide, and this is the gate material. You can close it. Next, where we have used the materials, it is already added in the parameter. You can see we have used the metal as the gate material, SiO2 as the gate oxide, and silicon as the remaining part of your what? Channel, source, drain, body. See, here in this case, we have considered the work function. As we know, the work function always the metal or the gate material, it has some work function value. We have considered the work function value of the gate material as 4.5 electron volt. It is given 4.5 means what? 4.5 electron volt work function we have considered. See, this is the command for your to define the work function of any gate material. Okay. See, this is the code. Like in this case, we have given the name as MOSFET 1, and this is the output file name. We have given MOS1, like this. And we have considered the drain voltage, drain to source voltage as fixed 0.05, and we are varying the gate voltage from minus 0.05 to your suppose 1.5 volt. We are varying the gate voltage from minus 0.05 to 1.5 volt, and we have considered drain voltage as 0.05. And this is your physics section that you have considered. Next, you run it. Okay, see, it is successful. Okay, so like this again, you can see the what? You can go to the extension to visualize the result and click on the run center as visual. This window will appear. First, you can visualize the what? Your drain current versus gate voltage plot. For that purpose, I have opened the .plt file. Okay. See, in the x-axis, you have the what? Gate voltage, outer voltage. You have to select the x-axis. And the drain current, drain total current in the y-axis. This is the corresponding linear plot that we got from the MOSFET device. This is the corresponding linear plot. If you click on the log y, then you will get the what? Log scale. Like the previous case also, see in the MOSFET, as you know, you need the on current and the off current. Where you will get the on current? On current means what? At the gate voltage of 0 volt. Sorry, at off current means what? At the gate voltage of 0 volt. On current means what? At the gate voltage of 1.5 volt. Because in this case, we have given the limit up to your 1.5 volt. And your drain voltage is fixed at 0.5. Suppose you click on the probe and probe it. Then if you write 0, then you will get the corresponding off current. In this case, off current is what? 2.66 e to the minus 12. Okay. Similarly, if you write 1.5, then if you click on the apply, then you will get the corresponding on current. 3.78 e to the minus 5 is your on current. Okay. Similarly, what you can extract the your what from this health option is the analysis. Okay, if you click on the analysis, you can see there is some option like your VTH, then ID set, saturation current. If you click on the VTH, then you will get the corresponding what threshold voltage for this characteristics. In this case, it is your 0.73 is your threshold voltage for this characteristics. And like the previous case also, you can extract the data, you go to the data, export and click the export the result. Okay. See next, I will open the TDR file. Okay. This is your .tdr file to visualize the remaining thing. See this is the corresponding, as you can see here also you can see the various characteristics like this. Okay. If you select on the what electrostatic potential, okay, this is the corresponding potential plot for the MOSFET. If you select the cut line, if you need to plot the electrostatic potential, see this is the corresponding potential for your MOSFET from source to the drain. Okay, this is from a source to the drain corresponding potential plot. See, suppose you need the energy band gap, then if you have to click on here, and as you can see here on symbol is there plot band diagram. You click on the band diagram and you get the corresponding energy band diagram for the MOSFET. As in the last class, Chittaran sir already shown the operation of the MOSFET depends upon this thermionic emission. As you can see here also there is some barrier to flow the electron. It has to cross this barrier. Okay. So like this, you can plot the other plot also like your here your electric field, then your SRS recombination or mobility plot also there. Mobility plot also there. Okay, if you click on the mobility, then suppose we are selecting the e-mobility. If you click on third line, this is the corresponding e-mobility for this MOSFET structure. Okay. And you see here from here also you can extract the data like export data and like this you can. Okay. So up to this is your demonstration on the MOSFET and the what PN junction. Whatever I told, that is up to this demonstration on the MOSFET and the PN junction. Okay. So if you have any query on this one, I think few questions are already on student. Any student, if you have any questions or any query, you can ask in this chat box, or you can ask directly also. You can turn on your microphone and you can ask the question. So sir, can you please show the FinFET simulation? Actually, the license whatever we have now, that is on FinFET, as you know, that is your 3D structure. But we have the license up to your 2D structure only. But 3D license, it will come within few days. In the next next time you have to show the FinFET simulation. But now we don't have the provision on the 3D simulation because we don't have the 3D license now. Okay, till only we have the 2D license on the TCAD simulator. So any other questions, any other participant, if you want to ask, you can ask on the chat box also, or you can ask. You can just turn on your microphone and you can ask the question. Okay, then no question. Yes, one student asked that, can you provide the sample code for TCAD? Yes, you see the MOSFET code, whatever I have shown here, this is the MOSFET code, whatever I discuss. The TCAD code also same only. As we know, in the tomorrow there is one lecture on the tunnel FET. You can see the TCAD structure. So in that case, what happened? In that case, in the TCAD structure, That is your PIN structure. Only what happens, source is P type. Only in this, the same structure you can use for your your tunnel pit also, but the source concentration you have to use the boron. Like we have used in this case MOSFET, both are arsenic, but in that case you have to consider the boron. And the code will be remain overall same only because the structure is a PIN structure, but the operation mechanism of the tunnel fit is different. That is depends upon the band-to-band tunneling. Okay. In the tomorrow class, there is one topic on your tunnel fit. In that one, you can see the structure. That is same as MOSFET. Simple. Your operation mechanism, of course, different, but structure-wise only your PIN structure. In this case, what it is your N plus I and N plus, but that is your P plus, like your P source, I channel, and drain. Okay, can you show the simulation of defects? Actually, yes, the simulation of defect. In the last, I think in the last lecture, I have that one. Yes, it is their demonstration on 30 November. There's demonstration of the tunnel effect. If time permits, I will show the demonstration of the tunnel effect in the last lecture. Okay. See any other question, any other student? Okay. Okay, then see tomorrow again we have the lecture. I think today is over. Then yes, today is over. Tomorrow we have lecture from 10 a.m. and the lecture topic is application of emerging tunnel effect, in biosensors, light sensor, and RF energy harvesting by Dr. Binda Humik from NIT Silchar. Okay. Then tomorrow you can join to the WebEx only at 10 a.m. morning. Okay. Okay. Any one questions came, how to analyze the performance of a device? Analyze RF performance. Okay. See the yes. In this TCAD simulator, you can analyze the RF performance also. But the code is different. Not this code. You have to run your RF you have to do the RF simulation. You have to do the RF simulation. You have to run that one, and you can extract your transconductance, gate capacitance, or like if you or your linearity parameter also you can extract, like your GM2, GM3. Those things also you can extract, and you can plot your frequency, etc. That means from this one, see one code is there. Code is different. Okay, in the next class, if time permits, I will show the RF performance. Then you can extract the RF performance like your transconductance, gate capacitance, or your cutoff frequency, etc. Similarly, you can extract the linearity performance also from the TCAD simulator. Okay. See, one manual is there. In that manual code is there for the AC simulation also. That is only you have to perform. Okay. Okay then. Okay then. Tomorrow we'll meet at what 10 a.m. Okay. 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 Thank you.